1, right? What would y be? Here's 0. Do we agree? Can you think of another UV point that would give me the same x and y? And negative 1, 0. Would that give me the same x, y? Is our transformation 1 to 1? No, right? Which means this idea of going back using a T inverse isn't going to work. But that's what we would like to take us back. Questions on how we did the transformation? No? Hi, it's Jay. I'm nervous. Okay, I'm going to go ahead and erase this. The whole point of transformations is that we've already done them and they've been really useful for integration. The transformations we've done so far have taken us from rectangular coordinates to polar, rectangular to spherical, and rectangular to cylindrical. What we need to talk about now is how we do double integrals using transformations. Now, I really wanted to prove in class why this was going to work. And I just don't have the time. I highly encourage you, though, if you have time, after we've gone through the formula, after we've seen some examples, sometime in like the next week to look it up. I will post my notes which will have it explained. So you can look at those, you can look at your textbook, but it's really interesting the reason why the formula we're going to get actually works. So essentially what we're going to be looking at here is if we have a double integral of f of uv dA over some region S. So notice we are integrating here in the UV plane, right? It's a double, so I have dA. If I want to do a transformation with this, what region will I be integrating over? I will not be integrating over S. How will I write this? I'm going to write this R. Is everyone okay with that? If you have a second, I want to make sure I line up exactly with what the book's saying. This is going to be F XY dA. Essentially, what we want to do here is talk about how we can write this transformation differently. That is, how we can actually write it all the way out. That is, how can we extend upon this? What we're going to do is, keeping this one right here, we're going to talk about how we can expand this out. That is, how we can integrate it not actually in the UV plane using S, but how we can write U and V using X and Y. That is, how the double integral of F, a function of X, using UV. Now, I can write this, if you guys would rather, as G of UV, where G of UV equals X. For shorthand, we can write it as X of U and V. Y of U and V, this is the same as writing 8 of UV equals Y. And here's where it gets kind of interesting. The problem with this is when you notice when we convert from polar to rectangular, when we go rectangular to cylindrical, rectangular to spherical, we always added something in, right? What did we add in when we went rectangular to polar? How about rectangular to cylindrical? I can wait. You are all wrong.
I mean, yeah, the argument.
What do we put in? You're overthinking it. What do we put in when we go from rectangular to cylindrical? R. What do we do when we go from rectangular to spherical? Rho squared sine phi, right? Okay, the big question is, where does that come from? Where does all that junk come from? And the answer is it all comes from this calculation of dA that is talking about in the domain that we're integrating. That all comes from a bunch of differentials. The differentials we're going to look at are the differential of x with respect to u, the differential of x with respect to v, differential of y with respect to u, and differential of y with respect to v. They are all partials. Why are they all partials? It's only semi-true. I'm kidding. Okay. Why are they all partials? Why aren't they all just normal friggin' derivatives? What is x a function of? U and v, right? It's got to be a partial. Same with y. Now, this is going to account for some of it, but what we actually really need here are also some differentials, right? Well, when I look at this here, I'm going to have plugged in u's and v's, right? And if I have u's and v's plugged in, what are my differentials going to be? It's going to be du dv, right? Exactly right. Essentially what we've done is we've said this is equal to this. I know x can be written as this function, y can be written as this function, and all of this junk here is going to help us approximate that if we go back to rectangular. Okay. This thing right here is awesome. It is so awesome. In fact, it's going to come up a lot, especially once you start taking higher level physics. This is what's called the Jacobian. There we go. The Jacobian is a really, really important concept, and there's a bunch of physics applications that we're going to be coming back to the last day of class. But for now, let's just go ahead and write up here. The Jacobian of a transformation x equals some function g of uv, y equals some function h of uv, is given as, what the heck do those things mean? We gotta think back. Not negative. We have a matrix, but what operation is that defined as on a matrix? You're all wrong. Determinant. The determinant, right? It's the determinant of the matrix with entries being your partial derivatives. So x delta u, delta x, delta v, delta y, u, delta y, delta v. Now, it looks really intimidating. Let's talk about how the order makes sense. First row are the partials with respect to what? Are the partials with respect to u and v? Bottom, u and v as well. What are the partials of? X, right? First row is of x. Second row is of y. This makes sense because my first variable is x in rectangular, my second is y. What is my first column with respect to? U. And my second is with respect to v, which makes sense because my first coordinate in x is u, my second coordinate is v. Now what I want to do is write out what the Jacobian is actually equal to. For this, we're going to need to remember all of our matrix stuff. How do we take 2 by 2 determinants? I multiply along what? I multiply along my diagonal. Am I going to go this diagonal or the second diagonal first? First one, right? I kind of gave that away when I said first one or the second one. And then what do I do with the second one? I subtract it off, right? Like that. This is what we call the Jacobian. The Jacobian comes from a really cool place. And so just to outline it really quickly, this thing right here basically makes up that infinitely small little area that we are integrating over. This makes up that dA. And the way it's calculated motion on a solid surface. So if you can imagine that I take a flashlight, I'm shining it down, and I cut a little rectangle out of cardboard. The flashlight, when I shine it down, is going to give me a rectangle on the surface, right? The problem is that rectangle, when I project it onto the surface, and then look at the surface from the side, is it going to look exactly like a rectangle? Maybe not if the surface is curved, right? It might look kind of funky. But essentially what this does is it gives me a way of calculating the area of that projection. Determinants come from what operation that we do with vectors. Cross product, right? And so essentially what we're doing here is this comes from the cross product of two vectors running along our parallelogram. That is along the rectangle projected onto my surface. Now most of you will still get confused, which is the reason we're not going to spend 20 minutes looking at this. But it's a really interesting concept. So if you can check out the notes sometime, it'll be very, very helpful. That being said, what we actually want to do here is we want to look at a couple examples. So I'm going to go ahead and I'm going to erase this. I'm going to erase it. And the first thing we're going to do is we're going to calculate a Jacobian. Given the transformation, x equals r cosine theta, and y equals r sine theta, find the Jacobian. I want you to think about this really quick. What transformation is this? It takes what to what? What do I plug in? Do I plug in x's and y's here? I plug in r's and thetas, right? So this transformation takes me from r and theta to, what will it give me out when I plug in r and theta? X and y, right? It takes me from polar to rectangular. Is this transformation one-to-one? No, right? Because each r theta does not give me a unique x and y. I can come up with multiple r's and thetas in the same one, right? Just kind of keeping that in mind. What we actually want here is the Jacobian, though, and to find the Jacobian, the first step is to find all our partials. And when I say all the partials, I mean all of the partials. First one we're going to find are the partials of x. So we'll find the partial of x with respect to r, and then we'll find the partial of x with respect to theta. What is the partial of x with respect to r? Going back to chapter 11 here. If I take the derivative of this with respect to r, it'll give me cosine theta, right? Because the r will drop off. Okay? Partial of x with respect to theta is going to be, the r is going to stay, right? It's sine, and is it negative or positive? Negative. Good way to remember once again is the graph of cosine in the beginning has a negative slope. Derivatives represent slope. Okay. Good there. We need y. Partial of y with respect to r will give me sine theta, right? Partial of y with respect to theta will give me r cosine theta, right? Look good so far? Questions? Okay, so if we want to find the Jacobian, all we have to do is plug into the determinant, right? Okay, across the top I'll run with x. So cosine theta, my determinant's enormous, negative r sine theta. Now run it with y sine theta. And over here, r cosine theta. How did I know I was going to put with respect to r in the first column? We have polar coordinates. I've got off like this, right? Polar coordinates have the first coordinate being r. Okay, so all we have to do is take the determinant of this jump. Determinant is going to be cosine theta, r cosine theta, minus sine theta,